Today we're going to talk about work and heat. These first terms on your notes are terms that you have seen before in different contexts for most of them, so I'm not going to really get into a description of these different terms and take up time on the video. You can look at those yourself and just re-familiarize yourself with a few of them. The same way with the laws of thermodynamics, I just kind of wrote them down here in the notes for you to have access to them as a resource. But we'll refer back to them as we need them in later calculations and things. Um, what I want to concentrate on in this video is dealing with the calculation of the energy in a system. When we look at the internal energy of a system, we can change that internal energy by either a flow of heat, and by a flow of heat, we're talking about Q. A flow of work, we're talking about W, or a flow of both work and heat. So when we look at an equation for this, we can see that delta E, as it says in this equation, is equal to that combined, um, um, the combined values of both the heat and the work for that system. So if we have Q, which again is heat and is measured either calories or joules. If we have a positive value for Q, that means heat has been absorbed, and negative value means that it's been released. The same thing is true for work. Work is also measured in calories or joules, and if we have a positive value for work, that means work is done on the system, taken into the system, done on the system. Negative value for work, and it's done by the system out on the surroundings. So anything taken in is positive, anything given off is negative in chemistry. So positive delta E, system gains energy, negative delta E, system loses energy. So let's look at this in a calculation. It says calculate the change in energy of the system if 38.9 joules of work is done by the system with an associated heat loss of 16.2 joules. The equation, remember, delta E is equal to Q plus W. The 38.9 joules of work done by the system means it's being done on the environment, on the surroundings, so that's going to be a negative value for our work. And we lost heat, it says right here, and that loss of heat means we're also going to have a negative value for Q. So delta E then is going to be equal to our Q value, negative 16.2 joules, plus our work value of negative 38.9 joules, and we get an overall change in energy of negative 56.0 joules. So that means this system has lost energy, and the energy has been given off. Obviously, it hasn't been destroyed. You can't destroy energy, but you can give it off. The next one, calculate the change in internal energy for a system undergoing an exothermic process in which 15.6 kilojoules of heat flows. Now think about what that means. If it's an exothermic process of flowing heat, that means we're dealing with a negative value for our Q value again. And if 1.4 kilojoules of heat is done on the system, then we're looking at a positive value for our work in this case. So delta E is equal to Q plus W. Our Q value, negative 15.6 kilojoules. And our work value, positive 1.4 kilojoules. We end up with a change in internal energy of negative 14.2 kilojoules. So not a difficult calculation, just have to keep track of what's positive and what's negative on the values that it gives us. So in this next part, we're going to look at an equation that's kind of derived from this system. A common type of work accomplished with chemical processes is that of work done to a gas through compression of the gas, or work done by a gas. If that gas expands, it does work on the environment. So we have this system here that we're going to look at. And to determine the amount of work involved when a gas expands or it's compressed, we use this equation. That work is equal to negative PAVE. That's what I call it. It's the negative PAVE equation. I know we have little acronyms and things for everything, little analogies that we use, but this equation then, P is in atmospheres, and our change in volume has to be in liters, and we end up with a work value of liter atmospheres. We've seen that before in our gas laws, if you remember, in a previous course. So also recall this equation, Q equals MCAT, another one that we have a cutesy name for, but Q equals MCAT. Q is heat, and that can be in either joules or calories. M is mass in grams, or it could be moles. So be careful when you see that. The specific heat is C sub P. A lot of the times we leave that subscript P out of our equation and just put Q equals MCAT, but it stands for specific heat. That can be in joules per gram degree Celsius or calories per gram degree Celsius, or it can be the molar heat capacity, which is joules per mole degree Celsius. And of course, delta T is our change in temperature. Now, this is important because this is strange but true. Kelvins can be used in place of degrees Celsius with no change in numerical value if we're talking about a change in temperature. Remember, we can get to kelvins by simply adding 273 to Celsius. A Kelvin unit and a Celsius unit, that should be a plus by the way, a Kelvin unit and a Celsius unit are the same change. Now, guaranteed, 1 Kelvin and 1 degree Celsius are not the same temperature. 1 degree Celsius, we'd be shivering. 1 Kelvin, we'd be dead and like crunched and stuff. So no, they're not the same value. But when you're talking about a change, they are the same. So keep that in mind. So our next problem asks us to calculate the work associated with the expansion of a gas from 46 to 64 liters at a constant pressure of 15 atmospheres. And they want the answer in both liter atmospheres and joules. And fortunately, they give us a conversion for going from liter atmospheres to joules. So our equation, W equals negative PAVE. It tells us that we have a constant pressure of 15 atmospheres. And it tells us that we have a temperature change going from 46 to 64. So we have a, always do final minus initial for a change. So we're going to end up with a positive value for this. What does it end up being? 64 minus the 46, we should end up with 18. I want to say 18, but it just be like me on a video to get the wrong value for a simple calculation. So 18 liters is our change. When we multiply those out, we get negative 270 liter atmospheres. So there's our liter atmosphere value. Pretty simple calculation. It also wants this value, though, in joules. So we want to use our conversion factor if we've got negative 270 liter atmospheres. And we know that for every 1 liter atmosphere, there's 101.3 joules. We end up with negative 2.74 times 10 to the 4th joules. So again, fairly straightforward calculation there. Okay, our last calculation, it says we've got a balloon that's being inflated to its full extent by heating the 89.3 kilograms of helium inside of it. In the final stages of the process, the volume of the balloon changes from 4 times 10 to the 6 liters to 4.5 times 10 to the 6 liters. under a constant pressure of 620 torr. The temperature of the balloon rises, gives us a temperature change from 23.3 to 79.4. And it wants to know Q, it wants to know W, and it wants to know delta E in kilojoules for the process. And fortunately gives us some conversion factors and gives us the molar heat capacity of helium as 20.8 joules per mole degrees Celsius. So it wants to know Q. What do we know about Q? Okay, we know that Q is equal to MCAT. So in order to have this value, in order to get this value, we need to know the either mass or moles, depending on what it gives us for C. Does it give us molar heat capacity or does it give us a specific heat? And it looks like, as we see up here, that it gives us a molar heat capacity for helium. So we're going to need to change that mass value of helium up here, 89.3 kilograms of helium. We're going to need to change that to moles. So let's do that first. We've got a side calculation over here. That's kilograms, so let's change it to grams, 89,300 grams. We need that in moles, so we need the molar mass of helium, which is 4 grams per mole, so 4.00 grams of helium per mole. And we end up with a value of 22,324 moles of helium. So we've got quite a bit of helium here. So that's our value that we're going to put in for M, 22,324 moles. Our C value, our molar heat capacity, it said was 20.8 joules per mole degrees Celsius. And we need a temperature change, and it's going from 23.3 to 79.4. Final minus initial, 79.4 minus the 23.3. We're going to get a value of 56.1 degrees Celsius for our change. So 56.1 degrees Celsius. And we end up with a value of 2.605 times 10 to the 7th joules. Now keep in mind that it wants these values in kilojoules, so I'm going to change this to kilojoules, and I end up with 2.61 to 3 sig figs times 10 to the 4th kilojoules. So there's my Q value. You also might want to be thinking ahead a little bit. Remember, to get delta E, we need to add Q and W. So this is one of the puzzle pieces we need to finish solving out this problem. Okay, so let's look at our next part of the problem, which is to find W. W, remember, is our negative PAVE equation. Now, we need a pressure. Remember that pressure, it said earlier, had to be in atmospheres, but they gave us pressure. Look at what they gave us pressure up here in. They gave us pressure in 620 torr. So let's get that 620 torr and let's change it to atmospheres. If you remember, there are 760 torr in 1 atmosphere, so it looks like we're going to have a value that is less than 1. We end up with a value of 0.8158 atmospheres. So let's plug that value into our equation over here. So we're going to get negative 0.8158 atmospheres times our change in volume. Now, I know this isn't correct scientific notation, but they're both times 10 to the 6th. So if you do final minus initial, 4.50 minus 4, you're going to get 0.5 times 10 to the 6th. This isn't an answer, so there's no reason why we can't plug this into our calculator and avoid making a stupid mistake. So I'm going to say 0.5 times 10 to the 6th for our change in volume. Final minus initial. And when we get that, we end up with a work value of negative 407,894 liter atmospheres. Now, on several levels, this is not going to work because it has to be in kilojoules. So we're going to have to convert it from liter atmospheres to joules. That's what our conversion factor is up here, and then on to kilojoules. So let's do that real quick. We got that value. Let's take that, and we know that there's 1 liter atmosphere for every 101.3 kilopascals. Kilopascals. I'm reverting to another conversion factor, 101.3 joules. That's going to give us a value of negative 4.13 times 10 to the 7th joules. But we want that to be in kilojoules, so negative 4.13 times 10 to the 4th kilojoules. So there's our work value in kilojoules. So finally, the last thing that we need to do is to take those two values and add them up to get delta E. So delta E is equal to Q plus W. We already said that Q was a positive 2.61 times 10 to the 4th kilojoules. That work was a negative 4.13 times 10 to the 4th kilojoules. So it looks like our delta E value is going to be negative 1.52 times 10 to the 4th kilojoules. So if you just do this systematically, step by step, doing your conversions as you go, the problem is very doable.